Okay, fine. Fine. So VLSI physical design training overview. We'll go through it one by one. Now this is the training overview. This is the agenda. So what we will be covering. So good. Okay. So this is the agenda.
Okay.
Yeah, you can go on mute. So this is the agenda. The physical design training overview. So what we will do is the main part in this is going to be floor planning, placement, CGS, routing, timing closure, easier cycle, and sign off. Okay, so these are going to be the main aspects of physical design. So what we will do, I will give you a quick overview as we go to each and every step of it. So in a chip, right? So we know people come up with ideas, a lot of ideas. So where do these ideas get registered? They get registered in say one of these forums in IEEE or somewhere. So for example, like PCI, USB, SERDES, DDR, etc. Blah blah blah. So many things are there. Now, once these ideas get registered in IEEE, there will be architects who sit and write the code for all these protocols. So after they write the code, so it is very good if somebody writes the code in binary language. It's going to be very tough. Okay, it will be very good because machine can easily understand it. But people have to write it in a very high level language. So the high level language is nothing but your Verilog or VHDL. I believe you all know what Verilog and VHDL is, right? Verilog stands for verifying logic. VHDL stands for very high speed integrated circuit hardware description language. It's an hardware description language to make the tool know what my design is all about, like PCI, DDR, and all that. Now, after writing the code, there will be a team for functional verification who will actually write the same code in their own language, because the code that we write in HDL is supposed to be matching the spec. For example, if it is a Bluetooth spec or a DDR spec, it's supposed to match that. If it is not matching, that's going to be a problem. Okay, so now there will be a functional verification team, like OVM, UVM, system Verilog, and all that. They will make sure that the code that is being written in RTL, in Verilog or VHDL, is compliant with the IEEE standard based protocol. Now that code has to be taken through the physical design flow, and that physical design flow towards end of it, taking it through all these steps towards the end of it, you will have something called as GDS, graphical data system stream. That will be given to the fabrication house and they will come up with the silicon. So I just told this in 10 minutes, but on an average, this will take close to okay, so that is what is graphical data system stream, and then they will manufacture it and give it back. So it's every portion of it is actually a big ocean, a big activity by itself. Now people go into different domains. Some people are very good in scripting. Okay, by their aptitude itself, they will have a lot of intention towards scripting. Some people are very good in layout. Okay, they can visualize graphics very well. So people who are good at appreciably good at scripting and appreciably good at graphic or viewing graphics, they can potentially take up the physical design flow. The physical design flow is nothing but after the code is written, there is a step called synthesis. So that synthesis is going to convert the entire code into small gates. Okay, these gates will be tied to the gates that are defined by the foundry people. The biggest foundry in the world is TSMC, Taiwan Semiconductor Manufacturing Corporation. There are many other foundries like global foundries, UMCs. Intel has their own foundry. Then many other companies have their own foundry. ST has their own foundry. Okay, but foundry is becoming a separate unit because people are not able to maintain the foundry as such. So they are selling out the foundry and they are going to be mainly into the fabless domain. Just like how Qualcomm is. Qualcomm is like a fabless company. They don't have foundries. They are tied to TSMC and they make amazing chips. Okay, all the Snapdragon processors, everything is being done predominantly by San Diego and worldwide teams, including BDC. Bangalore Design Center. Okay, so this is given to the foundry guys. The foundry guys give the silicon back. That silicon is again taken through series of steps like testing and validation and all that for multiple cost functions. So the first cost function is timing. The second cost function is power. The third cost function is area. Whenever I go to a shop, okay, I look for a laptop, and I don't know how many of you go and ask, like, what is the speed of the processor. I immediately go to the system control panel system and I'll go see what is the processor. I just not see what is i5, because the guys in the shop, they'll say it is an i5, but i5 which generation? 6200. Go and see what is the spec of 6200, what it is. Okay, so you will have to come to that stage as a semiconductor professional. You have to come to that stage that you can visualize. Similarly, Snapdragon 620, 820, you're buying a cell phone, just doesn't go looking at the frequency alone. Okay, so you have to get into the in-depth details. After completing of this course, you will have that idea of visualizing how much of knowledge you can put into getting the details of various semiconductor products. So these ones I am telling because these are common ones that we use in our daily life. Okay, but there are many more things other than this. Now, other thing which I want to tell is this entire flow, physical design forms floor planning to the ECO cycle. I have not covered the synthesis part. Synthesis is a separate portion. Anyway, in this program, we will be touching upon synthesis also, because the input to the physical design flow is actually synthesis. Okay, your code, your synthesis, and then your floor planning starts: placement, clock tree, routing, timing closure, and ECO cycles. Fine. So, let's go to the next one. So this is approximately around 12 weeks program. So we will be covering in-depth details of the full physical design flow. So it might go say a couple of weeks delayed also, or we can probably finish it if everybody, like, what I expect from this course is, the end of the course, you should be completely knowledgeable, or you should be clearly telling what is the flow and how you will be able to crack an interview. Okay, if an interviewer comes and asks questions, you should be able to. So no interviewer will be expecting 100% answer from you, even if you tend, because I have taken hundreds and hundreds of interviews, and my team guys have also taken. Now, if an interviewer asks a question, your tendency to the answer itself impresses him. For example, there is an option called clock tree here. So what is clock tree? Clock tree is nothing but building the frequency, clock frequency, into the design, and that matters in the running frequency of your chip. And building the clock spine is not an easy thing. And building the clock tree is one of the most important part in the entire physical design flow. Okay, now there will be a lot of questions, like timing questions, analysis questions, which the interviewer may put in front of you. Okay, so we don't know what question he's going to put. He may give an answer for one of the insertion delay, and through the other side he may give another number, and he may twist the question and ask in a different way. Okay, in such situations, if you know the in-depth, if you know the actual concept, what you can do, even if you do not give the exact correct answer, if you tend to the answer, that's more than enough. Okay, ultimately what the interviewer wants from the candidate is, can you join the company and make sure you get a profit for the company, and that's it. Okay, that's a high level thinking of every company, be it a product based company or a service based company, doesn't matter. Okay. I think we have to move to a bigger room. More guys come in. Anyway, for today it's okay. So, yeah. So, pardon me? Close the door and go, okay? the duration of the program is going to be 12 weeks. Okay, so course going to be completed in 12 weeks, and we'll be having training. So it's not hard and fast. It's like 12 weeks. Okay, a little forward, little backward. That's fine, because there can be some glitches in between. If there is a slippage for 1 or 2 weeks, then we will be adjusting that. So usually on an average, we try to keep it for 12 weeks. Okay, 12 intense weeks with 3 hours of session every Saturday and Sunday. So this itself is going to be covering most of the aspects for you. Okay. So tool access. There will be a 24/7 VPN access given to access the tool. So we will be having Synopsys IC compiler and Synopsys Primetime with Synopsys design compiler synthesis. So you will be predominantly using the IC compiler part of the Synopsys flow. Okay, you will be taking the netlist, you will be taking it through the labs, and you will be giving out the netlist. So the STA guys, that's the training for STA also. So the STA guys will be taking a netlist and they'll be taking it into prime time. Okay, so I'm not sure how many of you know, heard about IC compiler in prime time. Heard about it, right? IC compiler and prime time. IC compiler, now it's ICC2 after certain acquisitions and certain features that's been there from the other companies. They have merged into the IC compiler tool. It's called IC compiler 2 now. Okay, so that's the tool from Synopsys. Cadence equivalence tool is called Innovus. That STA tool is Primetime. Okay, and 90% of the industry uses Primetime. Most of the companies. Tempus is the equivalent STA tool that's from Cadence. Now, why do we need a separate tool for timing sign off? Because ultimately, I told you, every physical design engineer, end of the day, will be struggling to meet the frequency. So for us to meet the frequency, somebody has to sign off. They have to tick and say, yes, my design will work in this frequency after it comes back from the manufacturing fabrication house from Taiwan or wherever it is. That is why we need a separate STA tool as such. Okay. Now that's but you will be working on the ICC part of it, and ICC will be able to do static timing analysis, but not sign off level. Sign off level is much more deeper. Okay, it has got more features into it. I will be touching upon what sign off STA features are all about, but I will not be going into details of it, just like how I will be touching upon details of physical design program. Okay. So approximately 8 hours of practical session per week, and so we will be having two projects which we will be working on. So that will be on 28 nm node, and approximately in the range of 300 to 400K design. Okay, so now if after you complete the design, you will have to take through the labs. So once the labs are given to you, there will be a run script. The easiest way for everybody to do run it is take the run script, source run.tickle, done. Your GDS is going to come out. Is it going to help you anyway? No. What you have to take the initiative, open the run script, take the first command, put it into the shell, see whether it is running without any error. Good, thumbs up, it's running fine. Okay. Next, second thing is, before going to the next command, whatever command you have given, take it and put man, M-A-N. Okay, and see what that command does. You will be given user guide also. User guide will be there. You see what that does. If you do that for every step, okay, then imagine after you complete that entire floor planning all the way till your ECO cycle, what is going to happen? You're going to be much more knowledgeable than a person who just sources the run article on the shelf. You got it, right? So this is exactly what I would emphasize. Now it's left up to individual to take how you want based on your interest in going forward, taking the career in a physical design domain. Got it, right? Fine. But what the details of it I will be discussing. Okay, and practical you have to give lot of emphasis personally. to get more knowledge into it. Okay. Placement support. So students will be provided with 100% job on completion, 80% of the course. So most of the guys have job offers now who have got trained here, one or other. Others are in the pipeline. They will be getting a job because, as I told you, the shift is happening now towards India and China. Okay, and why we stand more than China is because of the communication skills. It's very important. Communications is one of the most important aspects of being a part of a team. You go, for example, there is a block given to you. You take the block, you start implementing the block. Okay, it is not that they giving you 8 months time. You implement the block and you finish it. No, there will be one more block. There will be other block. There will be 20 such blocks will be given to 20 people. What is going to happen? All you guys who are owners of the blocks, you will have to be closing the block, at the same time interacting with your project manager. Communication is very important. Now your block called block A, other block called block B will be talking to each other at the top level, at the subsystem level. When it is talking to each other, what you are giving is going to be input to other person. What he is giving is going to be input to you. Now communication is very important. Okay. Why communication is important? He may not be sitting in the next seat. He may be across geographies. For example, if you are working in companies like Qualcomm, the other block guy may be sitting in San Diego, or you'll be sitting in Austin, or you'll be sitting in Japan or China. Are you going to be communicating it really well? Okay, it is not written communication, oral communication. Everything is very important. So these are all secondary aspects when it comes to taking the career forward in physical design. Okay, so keep that in. Not only physical design, any domain, but I'm telling you specifically for physical design, you will have n number of interactions with quite a lot of people across various locations. Okay, now coming to the job, most of you guys will be, because we are quite connected to the industry well, so we will be giving guidance on what is to be done, and based on the involvement and the intelligence and the performance that you take through the training program, there will be an evaluation. And then if somebody asks, okay, I need so many guys, so it is left up to you for us to tell, like, okay, fine, so many guys are going to be there and these guys are good, so you can probably look into their profiles, schedule a discussion with them. If things go fine, please go ahead with giving an offer to them. So we will be working on that towards the end of the program. Okay. Then assignments. Whatever we study here, okay, it has to be evaluated. It's very important that we have to go through certain assignments. Okay, so you have to know, if you prudently take notes, and as I told you, if you start maintaining that so-called Bible, then this assignment is going to be cakewalk for you. Okay, you will start adding more to what has been asked in the assignment. Okay, so I can give you one example. I'm not going to mention the name now. Once the training program starts, I'll give you an example of a person. Okay, I was really astonished the way he actually came up with various things after the program was over. Okay, he clearly made note of everything. And now see, when we started the career years back, okay, like 18, 19 years back, what happened was Google wasn't matured. If I go to Google and if I put property synthesis, hardly some 500 pages will come. Okay, and that too irrelevant material will come. I will not be having much details on what it is. Now if you go, you have wealth of knowledge. Okay, but if you have wealth of knowledge in it, you should know what is to be taken and read. Okay, so simple example is, why am I having cold and cough? If you go and put first thing, you have cancer. Okay, it doesn't mean that you have cancer. Okay, similarly, what is relevant? If you know what it is, you can go and actually take. The point that I'm making is, when I'm giving assignments to you, go through it in depth. Everybody has access to internet, whether through mobile or through laptop. Go through it, see what it is, take it, and then solve it. If you're not, that is the best way. Okay, you getting into the fire and solving it. If you're not there, there are WhatsApp groups that we created. Pose the questions, we will be discussing the answers, or make a note of the questions. Come first half an hour in the class, open the questions. Okay, you tell that, sorry, I'm not able to understand. Let it be as simple as what is setup, what is hold, what is transition, what is cap, what is derates. Let it be as trivial as that. Doesn't matter. Okay, but open the questions, because if you know what it is, then slowly, even if you emphasize what you know further and further, it is going to strengthen you. Okay, so assignments are one important part in that. Okay, so we at least 5 to 6 interview opportunities we will be helping you in getting. It's left up to you how prudent you are in getting into the opportunity, or closing the opportunity, that left up to the individual. Okay. So here, so it's predominantly from the head of the institute. So this slide, as it's obvious. Now we will be working with Synopsys tools, which most of the people in the industry want to. So tools are not cheap. Believe me, tools are absolutely not cheap. And I was with Cadence and many other companies, so I know how these companies are in terms of because a lot of R&D activities also go into the tool. Okay, a CAD person does not get evolved easily. Okay, computer aided design for electronics. Okay, the EDA person, electronic design automation person, does not get evolved easily. So there's a lot of maturity in terms of software, lot of maturity in terms of electronic thinking. Everything goes into CAD. So now the world's best institute for CAD is Carnegie Mellon in the US. Okay, so they churn out a lot of excellent CAD personalities, CAD PhDs in the world. They come up with CAD tools. So the point I'm making here is CAD tools are very expensive, and in spite of that, what we do is we try to make sure that it is affordable to most of the folks, so that at least you guys can come up and then make sure the industry is up. Semiconductor industry. Okay, why should Taiwan be up? Okay, why should US be up? Later on, you might move to US. We don't know. Opportunities can happen 5 years, 6 years, 8 years down the line. Not sure. Okay, but at this point of time in this country, can we do that? Yes, we can definitely do it. Okay, and the need is there, the vacuum is there, and just point blank we cannot go and fill the need. We have to go fill the need with the right stuff. Okay, that's why we have to go with the right set of training program. Okay, and the reason why we are having it at a low cost for this, there's some statistics given here. You can go through those statistics in detail. Okay, and that will help you. And there'll be a WhatsApp group. Okay, so I'll be the person who will be involved in that. Usually what I will do is I will not answer immediately. Okay, I will not answer immediately. After a question is, there are n number of questions that gets added, because anyway, I will also be quite busy with all my work. I will wait for somebody else to answer. Okay, and let that somebody who is answering, let that answer not be perfect to the point. Fine, no worries. Okay, and I will encourage each and everybody to answer it. Okay, and I will take a pause. I'll take some time towards the end of the day or towards the second half of the day. I will see what all answers came. That then I will know. Okay, guys are able to think. Okay, then I will say, okay, probably we discussed this, we discussed all this. Now, this is what, okay, your thought was, but actually it should be a little different. Okay, or what you did is correct. Okay, same way. I will just make sure that things are fine. So I keep more this WhatsApp group active also. Okay, so yeah, as I told you, it is going to be on the weekend. It is not going to be on the weekdays. Okay, because weekdays is going to be quite hectic for most of the guys, as well as for the trainer also. So whenever I mention me, it is just not going to be me alone. It is going to be the trainer, whoever it's going to be, who is going to train. Okay. So any doubts in this slide, you can probably go through. This is predominantly related to the logistics and the facilities and all that we are providing for the program here. In fact, for the session that we are giving here, the fees has to be at least at par what everybody else takes, like 4x to 5x more than what it has to be. Okay, but really there is a need to see. Now I have a knowledge. Okay, what happens tomorrow if I die out? Okay, I mean it won't happen probably willingly. Now that entire knowledge is gone. Okay, So sharing knowledge is one of the best things that anybody can do. Anybody. Okay. So one small quote which I can actually give, probably you might have also seen. Merkel, German Chancellor, right? Vice Chancellor. So she makes sure that the perks and the salaries of the teachers and professors are much higher than the perks that are given to other people. Okay. Similarly, one example. So I was in Taiwan also. I was in Taiwan for close to 8 months. There's one example. I went to a community and I was looking for people who can talk to me in English because I was not finding people who can talk to me in English. Okay. And I was getting so frustrated. Even without food, I can live, but not without talking. Okay. So I went and found a couple of guys, okay, who can talk in English. Few of them were from Canada and few of them were from UK. So I asked them what they were doing. So they all have been deputed in Taiwan by the government to teach English. Okay. And believe me, their salaries were much more than our salaries. Point number one. Point number two, whatever salary they are giving, there is an equivalent same salary that is being given by the Taiwanese government. Okay. The reason is they have to come and make sure these countries develop in language first, because they are advanced in other things but they are not advanced in communication. Okay, that is where we stand up above them. Okay, so that is why they are paid so high. Okay, anyway, after that then we started interacting and a lot of things happened. Then I went and asked them, is there a possibility of joining the company or the organization, being a part of India? They said no, there's a need that you have to be from an native English speaking country. Okay, anyway, keep all that aside. So what I'm telling is the fees and all that, right? Coming to the fee side, we want to make it affordable to everybody. Okay, and make sure you fill the void and gap that's coming in the industry now, at least the shift that's happening in the last 2 years. And that is what is being captured predominantly with the fee structure and other things that's over here. Okay, so most of the 23% of the learning happens attending course lectures, because you should know what to do. Okay, if you have the user guide 1300 pages, I will sleep for sure. If somebody gives me 1300 user guide, go through it, you will know physical design. Definitely we'll just sleep off. Okay, the most important part is get involved in every session. Create your Bible. Again, double quotes, I'm telling you, create your Bible. The Bible is nothing but the book that I'm telling. Each and every word, if you make a note of it, and if you go and see, I don't know this word, you told some word, I don't know what it is, tell what it is again. If you make a note of it, that's more than enough for clearing your interview. Make a 200 pages Bible. So most of the things happen in the course here. So remaining learning happens by working on assignments and the labs. Labs, what happens is VPN access. We'll be having, say, for example, 30, 40 guys are joining the program. We'll be having 8 or 10 VPN sessions. So you have to multiplex. Some people will be working in the daytime, some people will be working in the evenings, some people will be working in the night. So you have to multiplex and take. So as and when you will be having preference, how to do, what to do when, and all that. So you will have to take yourself. And in the class, we will be getting through the lab session. I'll show what to do. Then it's left up to you. You have to keep your hands onto the shell. Okay. Then, in case if I fall sick, what, there will be a discontinuity. Okay, I came from floor planning, I came to placement. Okay, first part of CTS I missed, then I went to the second part. First part of CTS, why I missed? I fell sick. I missed one session. What to do? There will be recorded sessions. Okay, prudently, before coming for the next class, okay, have your earphones plugged in, go through the recorded session, understand what it is. Okay, if you're not able to understand, make a point note of it, come for the next class, clear that, sit for it, so that it will be a continuity. Okay, the continuous flow. This is nothing but a flow. That is why we call it as physical design flow. I will not touch ECO, then I will not touch floor plan, then I will not touch CTS. It is a flow. Okay, by the end of it. Okay, so what if I miss? You can have recorded sessions. Okay, so projects, can it be updated on the resume? Very important part. So once you complete it, okay, so different people will have different resume. That's why in the beginning I asked, how many of you from the electronics background, how many of you have worked associated with physical design? Okay, associated in this like physical verification or synthesis or DFT or static timing analysis or PCB design or something. Okay, so how are you associated? So we have to make sure that you have your resume added in a way where it is going to show that you have experience of so much, like say 1 year, 1.5 years, or 2 years. Okay, after putting these projects, and believe me, if you come and stand and then another person who joins an MNC comes and stands, okay, if you benchmark the person who completes the program here, okay, and the benchmark the person who is standing here, that person might have got a offer, okay, that there will definitely be a differentiator between you and the person who is coming directly after finishing their college or program, okay, and your thought will be in that stream, not only to get a job, not only to clear interview. Clearing interview, 1 hour's time. Interviewer comes. Depends on interviewer's mood. Okay. And depending on interviewer's profile. If he is a physical verification, he will ask 90% of the questions in physical verification and judge based on that. If he is a floor planner, he will ask questions only on floor planning. Okay. But we will cover everything so that you touch upon all these, your thoughts are fine. Now, after clearing interview, you go get a job. Good, happy. Okay, job offer, everything is good. It doesn't stop there. Okay, after 6 months, what are you going to do? After 1 year, what are you going to do? 2 years, 3 years, 5 years, are you going to scale up in your career? Your seed is actually going to be put from here. Okay, you have to build on the seed. Okay, then later on, when you start the program, when you keep going up, then once you start the job, you will find so many designs in front of you. You will be forced to do multiple designs. Okay, there is no option for you. Then all these lab sessions are going to be irrelevant at that point of time. It's just an entry. Okay, but whatever we are teaching, the concepts we are touching upon, the complete fundamental concepts as well as the industry concepts which we have gained through these years, whatever we are going to give to you, those will help you scale up much better than the person who is going to stand next to you if there's a benchmark that's going to happen. Okay, so that's going to be how the program is. Yes.
I'm working as a network engineer.
Okay.
So can I keep this experience 2 to 3 years?
Network in the sense, what is the language that you use?
Networking.
Networking. Okay. Not much. But are you from electronics background?
Yeah, I'm an
EC engineer, right? We have to capitalize on that only. But networking may not be that much correlating to a physical design as such. But since you are from ECE background, it will be good that you can appreciate most of these concepts, because microelectronics is nothing but electronics. The only thing is you are looking at a smaller level. Okay, current is flowing from this point to that point. What is the potential difference? Potential is 230, potential is 0. Okay, so difference is 230 minus 0. Okay, similarly here from the VDD to the load is nothing but the opening of the gate of the next transistor. Okay, it is going to be 0.920 volt. 0.9 is potential difference. You should think in that level. That is what microelectronics is all about. And I will clearly give you with each and every diagram and flow and current flow, each and everything. I will tell you how it is actually happening at the transistor level. Okay, so most of these institutes, what they do is they just give the commands and then they go forward. But they will not go into details. Once you learn such things, there is no way you can forget it. Even if you try to, you will not. Somehow you will remember it. Okay, and we will come to that state. That's how we are going to do it.
So can I take these 2 years of experience?
Okay, now you cannot directly give it. Okay, if you're taking an example of network engineer, you cannot directly give it. But there is something called as um, uh, people. For example, at least I do that, or I tell my guys who are the team to do that. What we usually do is, if somebody is working in another domain, okay, and they have got 1 or 2 years experience, they would have got to know how the execution of project works. For example, timelines, milestones, okay, excepting the implementation part, which you will be taking out of the course here, the other things you will be much familiar with. Okay, so that is also one important factor when somebody looks at hiring a person. Okay, that is why I'm telling, attitude of the person who goes for an interview, and attitude of the person who goes for an interview, and the communication skills. So if you are working for 2 years in domain similar to this, then there's some takeaway, but not complete takeaway. The gap you have to bridge by taking up this program. So to answer your question, in your resume, it will add little more weightage when you say that you are a network engineer. So, but on a case by case basis, okay. So there was another person, I don't want to mention. I can probably tell you later, who was in the similar stream. Okay, after completing the program, okay, what he did was he had his resume changed accordingly, and now currently is working for a MNC through a services organization. Okay, so we will guide you through that, how we can actually take that. Okay, so on a need basis, we have to go on individually look into for everybody. Okay, on the need basis, your resumes have to be looked one after the other, because everything is going to be varied. Not everybody's resume is going to be same. Okay. Fine. So I touched upon all this digital design. I'll give you the name of the books. Okay. If you don't know what you need to go through in physical design and all that, I will tell you. It's left up to you to get your digital design fundamentals clear. If you come and tell me I don't know what an AND, NOR, or inverter, buffer, flip flop does, then it is going to be very tough for me. Okay. You should know these things fundamentally. If you know these things, then getting into the program is going to be much better. Okay, and I'll give you details what are the things that you have to learn with books and each and every part. So again, this is related to the training FAQs, usually what people ask. Okay, so this point is very, very important. Okay, so a lot of people ask this. I have so many questions coming in. Okay, so the number gets routed to my number, and then I have to keep answering so many people. They ask me, I'm working here. Okay, I want to move to physical design or front end. Okay, what should I take? Okay, so just because you have to come for the program, I will not tell, please come for the program, do this. No, I will not do it. Okay, again, you have to touch yourself and know, is your aptitude, do you have the liking for electronics? Point number one, you have to have liking for electronics. Okay, if you do not have a liking for electronics, it's going to be tough. Okay, one of my classmates, okay, he just hated mathematics and physics. Okay, he hardly passed. Okay, and now he is in Cleveland. Okay, and he is a PhD, and then he is doing his postdoc in Cleveland, one of the universities there, Maryland or somewhere. Okay, and he is in biotechnology. Okay, now he's using a little bit of mathematics on course of thing he learned. Same way, he was very clear what he wants to do. But for me, if I get jitters in my mouth if I look into biology. Same way, why I'm telling this is, you should have aptitude for electronics. Okay, many people now, I don't know whether you know this term called IoT, Internet of Things. Okay, that boom, especially with the kind of um, development that's scaling in India. Okay, opportunity, solutions, so many things are coming up. Intel, they're coming up with a platform called Galileo. They have a processor sitting in called Edison. IBM, they have a platform called Watson. MediaTek, they have a platform called Linkit. ThinkWorks. There are so many platforms that's coming in IoT. Why they're coming up with a platform? Because everybody, they know, I have a problem. When I'm walking in the road, I have a problem. The car is going. Can I map the road? Okay. And can this data be sent up? How to map the road? You have a small camera. You have proximity sensors. So many things. How to take this? How to connect to your general purpose IO ports? And then how to take the back. So all these are macro level, but what is working inside is the processor, and for the processor, who has to do it? Entire VLSI design forum. For in that, you have to be a part of it. Now, if you have to be a part of it, do you have the aptitude? Should I take it? Now, some people are very good in scripting. Okay, they can do very lot of things on the shell. Okay, close their eyes, put leg over leg, and then they start. If else, then blah blah blah. They keep going, and they know in and out of scripting perfectly. They'll do. But when it comes to graphics, it is going to be tough for them. They will not do it. I have seen it is. It doesn't mean that the person is not good and in say the concepts. He'll be good in electronics, but he cannot view graphics. Okay, so it's not necessary that you have to completely know graphics. Okay, even if you have not got an exposure, once you start using the labs, you will definitely know that. If you are very good in scripting, or you have knowledge of protocol, okay, like somebody came up with Bluetooth. Now something is there called BLE, Bluetooth low energy. Why BLE people have come up with? Mainly for IoT. One device should talk to another device. My watch should talk to my laptop. Okay, my cap should talk to this one. So there are many things. I'm not giving examples. There are like plethora of opportunities in the IoT space. When it comes to that level, do you have that thinking? Okay, now if you have the aptitude to think in the protocol level, then front end is the option for you. Okay, but if you want to implement it, then back end is the option for you, back end or physical design. Okay, both are equally good, both are challenging. Somebody develops that, gives it to you, that's all, his work is done. It's left up to you, you take it through and then give the GDS out. Okay, and one portion of it called static timing analysis, that name last name analysis in static timing analysis, is one important very big factor. Okay, lot of thinking, lot of involvement is needed in it. Okay, if you have an aptitude for that, yes, physical design is good. Added to that, the current job opportunities in physical design, the vacuum that's created for a lot of physical design engineers that's needed. Okay, so many companies budding up mainly for physical design. Okay, um, Taiwan, Singapore, UK, US, quite a number of opportunities are there. UK, US, maybe for visa reasons, they might have. See, they need people, because I know I've been working in all these places. They need folks, especially folks who have been trained so well in VLSI, the entire stream, but they don't want to take because of various reasons, obvious reasons. Okay, because of cross country issues and all those visa related things. But the requirement is there. Okay, left up to you whether you have to go for front end or for back end. Okay, so physical design is one of the main things in this program. Okay, so the last 3 points I have mentioned that I don't have to reiterate that. You know what it is. Okay, so these are all the prerequisites. Predominantly, you have to be an electronics background. You have to appreciate it. Okay, otherwise it's going to be tough. Okay, there are many guys who have completed MTech, microelectronics, VLSI design. They have come for the program and they have got their placement down. And people who want to sharpen their skills, okay, in physical design and in STA and in other associated domains, they can also come, be it a faculty in a engineering college or whoever it is, because getting it from the industry, people who are working in the industry, is completely different from getting it from somebody who is been working as a faculty or working in a training program. Okay, so we somehow make time to come and help. That is why I keep telling, I don't, if I perish tomorrow, I don't want to have my knowledge perished. Okay, let it go to like say some 500 people. I let those 500 people come up. Okay, so let them also spread. Teaching is one of the best things that somebody can do. Okay, I would put it much above being a noble profession of a doctor. I would definitely put it that way. Okay, so anyway, these are all things which we clearly touched upon. So keep one thing in mind in physical design. Three things are important for you. Okay, you have to meet. You have to struggle to meet three things in your project. Project maybe 6 months, 8 months, 10 year, 1 year, 1.5 year, 2 years. Okay, timing first, power second, area third. Keep these three things in mind. I have to meet my timing. I have to meet my timing. I have to meet my timing. Every time that thought has to be going in your mind. I have to meet timing. I have to meet timing. Okay, that's it. and second thing is power, and third thing is area.
One thing, sir.
Yeah.
I have done some ads in the office that they require the people for like 20 mm, 28 mm, like 40 mm. What is the difference between 40 mm?
Okay, so just usually what happens is once the program starts, I will be giving you the details of what it is. Just because you asked, I'm just going to tell you. So you asked a question like, what is 40 nm, what is 20 nm, what is 10 nm, etc. Right? So earlier it used to be 250 nm, 180 nm, 30 nm, 130 nm, 90, 65, 40, 28, 14, 10. Okay, currently I'm involved in 10. Okay, so what it is nothing but your channel width. Okay, so again, take your English dictionary. Semiconductor, everybody knows what semiconductor is. You're all interested in taking a program in physical design. Okay, what is semiconductor? Now take the word semiconductor, keep it in front of you. Look on the left side, you see insulator. Look into the right side, you find conductor. Okay, insulator doesn't conduct, conductor conducts. Okay, semiconductor partially conducts. Why does it partially conduct? It partially conducts because there is something called as a gate, that is called the polycrystalline. Okay, so what happens to the gate? You give a current to the gate so that the gate opens. Again, gate is a normal English term. Gate, you open the gate, people come in. You close the gate, people don't come in. Same way. Okay, you have a gate, you give a current, gate opens, then the source current will flow down to the drain. Okay, similarly the gate opens, the current flows down from the drain to the source, which is VSS, to the ground. So you either have a 1 or you have a 0, and computer knows only zeros and ones. You know that, right? Zeros and ones is nothing but sourcing and sinking of current. Coming to your point, the gate. Okay, after you give the current, what is the channel width? Okay, the channel width depends on the speed at which your current sources or the current sinks. Okay, for a transistor. Now, if the channel width is really big, you need higher potential for it to go and actually open the gate, or a longer time. Now, if the channel width is smaller, okay, the time taken for the gate to open is very small. Okay, that is why 10 nanometer designs are very fast compared to a 65 nanometer or a 90 nanometer. Okay, same inverter you have on the left hand 10 nanometer, on the right hand 90 nanometer. Okay, 10 nanometer will open the gate in 5 picoseconds or 10 picoseconds, whereas in 90 nanometer it may take 40 picoseconds. Okay, now your entire design, so 5 to 40, or you say 10 picoseconds to 40 picoseconds, there is 4x difference. Okay, will that 4x difference involuntarily have an impact on your frequency? Yes, it has, and that is what physical design engineer have to do. So to answer your question precisely, there is nothing but channel width, as simple as that. If you go to Google, they'll tell. But we will go through all the details once we start the program. We will go through the in-depth details of what it is. So in Outlook, if somebody is asking you, have you worked on 10 nanometer, 8 nanometer, 10, if you tell I worked on 180 nanometer, people may not accept you. Okay, but if you tell you worked on 65, 40, 28, 10, then yes, because all this falls in the same ballpark area. If you worked in 40, you can extrapolate your thoughts to 20 nanometer, to 10 nanometer, or anything. It doesn't matter. Okay, only thing is the scaling happens differently. But now the architect, he has a big job because he has to reduce the frequency. There is something called pipelining. I don't know whether how many of you have learned about know about pipelining and retiming and all that. Okay, all this will come in the course that we do. So you have to break the path and then you have to put it. So architect will have a little bit of a day to change the design which worked in 90 nanometer and to make it work in 10 nanometer. Okay, so that's the answer. Channel width. Come up with questions and we will be able to answer various things. Okay, if you're silent, it doesn't help to you, to me. Okay, sometimes I may start yawning. Okay, because I will be talking. How long can I be talking? I need interaction, right? So I want interaction from everybody. That's why I'm telling, I will not be bothered even if you have the most trivial questions. Open up the question, please ask. Okay, it's very important. Okay, so here Reading the netlist. Who gave the netlist? Architect wrote the code. Synthesis did the synthesis. Mapped it to TSMC technology library. Optimized. I finished my setup check. Setup timing is good. Hold I will not be checking at this point of time. There is a definite reason why a hold is not checked here. Why only setup is checked. Okay. After CTS is hold. After CTS is when hold is checked. Okay. That netlist is given into floor planning. Then that will be given into initial placement. Then it will be taken through routing. Then it will be taken through CTS. Then it will be taken through cost estimation. What is cost? We know English meaning of cost is nothing but money. Everybody. Okay. Ultimately, it boils down to cost for a chip is timing, power, area. Timing, power, area. Cost function. First is timing. Second is power. Third is area. Some people associate TTM also as a cost. What is TTM? Time to market. Okay. So there is a race. Lot of races happening between various companies. Broadcom, Qualcomm, Nvidia, blah blah blah. So many companies are there. Okay, who brings it 1 week before? Done. That 1 week of gap is more than if you bring a product 1 week in advance, that goes into the market, 10,000 products sold, that itself is a marketing. Then 1 week later, other product comes, doesn't matter. So TTM, time to market, is also one of the cost function. Okay, so anyway, this may not be of that importance to us unless you are into the project management stage, which you eventually will do in your career later. Okay, so then routing. So routing has got various routing. So there is a global routing, there is track assignment, there is detailed routing. Various stages of routing is there. Okay, detailed routing. Then again, cost function estimation. What is the cost function? Timing, power, timing, power, timing, power. Then lot of cleanup needs to be done. What is the cleanup? There's something called as physical verification. Okay, what? Echo. Yeah, I mean, we usually don't call it as echo. We call it as ECO itself. Just like if you go and tell SAP, people don't like. Okay, even if you go to the labs there, they prefer themselves to be called as SAP labs. Okay, they don't call it as SAP labs. Okay, but many people tell. So you have to tell the word as it is. Okay, that's how we have been, brought up in this domain all this while. So ECO. Okay. So engineering change order. Okay. So that's right. So after that, we have to go for the ECO stages, physical verification. That's one important factor. Okay. And then timing cleanup. Okay. So all this comes as a part of the flow. Okay. Finish everything and then write out the database. This database, after your say 8 month, 1 year, or 2 years, I'm talking about your work in your company, you will be giving it to the fabrication house. They will take it for the fabrication. So this flow we will be actually going through. This entire flow we will be going through in the physical design, and we'll be touching each and every aspect in detail. In detail, each and every aspect.
So the partitioning is not a part of
Which one?
Partition.
Partitioning is a part of it. That's what. So when it comes to floor planning, I will be touching about partitioning also. So your full big i5, i7 chip, idiot tool will die. You go and take your entire design, put into a tool. Even if you have a small partition, the runtime for floor planning, runtime for placement, runtime for CTS, runtime for routing is 40 hours, 50 hours. You make a change, you fire the run, wait for 50 hours, it comes out. Then you find that what change you made is not what you expected. You go make the change again, another 50 hours is gone. 50 plus 50, 100 hours gone. How many days gone? So do you think it's a viable solution? No. Cut it. Partition it. You take a partition. You take a partition. You take a partition. Top level person, as a lead, as a project manager, I have to make sure all the partitions that you give have to be talking. And there's a very important factor called budgeting. Okay. So at this level, you will not be doing anything on the budgeting side. Okay. At the initial phases of the course, budgeting you will be doing only when you go to the next level. Okay. Once you know the block level, all the details of block level, then you will go for the budgeting level. Okay. Because budgeting is nothing but it's an eagle view. Okay. You see from the top, block A, block B, block C, block D, how they are talking to each other. How internally they are talking, I'm not bothered. That's your headache. You finished. How they are talking to each other. That's what my problem is. Okay. That is what partitioning, and that comes in that planning phase. Okay. And we'll be going into details of partitioning, budgeting. Okay. Subsystem level. So block level put together, subsystem level put together, chip level. That is what we will be discussing. Okay, fine. So fundamentals of STA. Usually, what I do is I start the program with STA because, as I told you, all the struggle till the end we will be doing is mainly to close timing, timing, timing. So you know what you have to do, learn that first, and then get into the struggle. Okay, you have your armor, you have everything ready, and then get into the flow. Okay, so whenever I tell get into the struggle, don't take it in a negative way. I'm telling get into the flow. Whichever it is, you have to sit and learn what it is. Start with the STA, understand what it is, and then go and make sure your first cost function called timing is met throughout the flow. Okay, inputs, sanity checks. Okay, so as I told you in the previous slide, okay, you're reading a netlist. Okay, some guy would have given me the synthesis. He is a part of the synthesis team. What if he gives you the garbage? You will take in garbage, you will start running garbage. Okay, if you start running garbage, you will also not converge. Okay, at the same time you will make sure the interface person also not converge, does not converge. Okay, the entire system is going to get caught. So there needs to be some sanity checks. Okay, whatever you're giving, is it good? If it is not good, give it back to them. You tell what it is. So we have to learn about what some sanity checks are. Okay, that's what is sanity check, inputs and sanity check. Libraries very important. TSMC, UMC, GF, they'll be giving you libraries. Okay, all these cells finally have to go to TSMC to get manufactured. They will create the library. There will be spice model. Okay, there will be some models called spice model, which is transistor models. Okay, they will do characterization with the spice model and they will come up with the tables. So there are tables like NLDM, CCS. Okay, non-linear delay model and composite current source models. You will have to use those libraries in the form of .lib, .left, .gds, then technology file, TLU plus, NXTGID, blah blah. So many variants are there. You have to use those libraries, and whether those libraries are all available, whether one cell is missing in the library, it's very important. So sanity check of the libraries, technology files, netlist, constraints, double, triple, four quotes I have to put in thick font, timing constraints, very, very, very important. Okay, you have a design, architect has told that your design, he has written the code. Okay, there is a processor sitting inside, it has to work in 2 gigahertz. Okay, how will you tell the physical design tool that it has to work in 2 gigahertz? Okay, you have to constrain means you have to tell do it in this time. 2 gigahertz means what is the time period? 1 by 2 into 10 power, correct? Take it, that's the time period you have to give. Now you have to create the constraints file. The constraints file is going to be called as SDC. Okay, so in SDC, create clock, create generated clock. Okay, set clock groups, then false paths, multi-cycle paths, input delay, output delay, mainly for partitioning and budgeting. All these things individually you have to give in the file. Once you give all these things in the file, then that will be the golden guide to that. Okay, so if you do not give the proper constraints, what tool is going to do? Whatever you have given me, I'm going to work based on that. That's what the tool is going to do. If you give me relaxed constraints, I'm going to be relaxed. If you give me tighter constraints, I'm going to work harder to meet the timing. Okay, constraints very important. I'll be emphasizing day in and day out on multiple variants of constraints. IO placement. Okay, placement of IO cells, etc. Okay, so input output. Why floor planning? Okay, then different forms of floor planning. Not typo, sorry about that. Floor planning, area calculation, how to calculate the area. It's very important to calculate the area. Area is also a cost function. Silicon cost is very important. Okay, so one point I would like to make here when I say silicon cost is very important is people think chip is nothing but silicon. Okay, it's available everywhere. I turn left, I turn right, I find silicon. No, why it is very expensive? Why only Taiwan? Why people are not able to do it everywhere in the world? It's the same silicon, no problem. But the process is what takes lot of energy, lot of technology, lot of people's mind and analysis. Okay, that is what it is. So there's a process called Zakrzewski. The person is from some Russia or something. He was a scientist who found that out. You have to have crucible. You have to have put it. You have to have these put in that. There should be an ingot. The ingot should actually take it. So polycrystalline become monocrystalline. You slice it. You get a wafer. You cut the wafer, make a chip out of the wafer, and all this. If possible, during the course, I have a video also. So through one of my known sources, and it's available on YouTube. I'm not sure about it. I can show that video. It's probably like 10 or 15 minutes video. I can show that also, taking through the process. Okay, so that you get a feel. That's why I want to make everybody a full engineer, full semiconductor professional. Okay, so that is what area calculation is. The point that I'm making here is that silicon cost is expensive, very, very, very expensive. Silicon cost. It is not.
Yeah. The cost is depending on number of gates or total area.
The silicon area, so it doesn't depend on the number of gates as such. Okay, so if you have a very big die area and if you have very less number of cells in it, then we have something called as utilization. Okay, the utilization may be very low. Okay, if the utilization is 10%, 15%, 20%, and if you have a full die, it doesn't matter, they can manufacture it. Okay, but you have to give that full die cost for them. Okay, instead of that you have to reduce it. But if your companies like Qualcomm, what they do is it goes neck to neck. Okay, the utilization will be 70%, 80%, 90%. If the utilization is getting really higher, the problem is all your interconnect routing will be close to each other. You will have a lot of PV problems, physical DSI problems. Okay, physically you will be moving, that will disturb timing, clock gets disturbed, timing gets disturbed, so power gets disturbed, so many things happen. Okay, in such situations, the number of gates or number of cells in the design plays a bigger role in the area. Okay, so people who have their own fabrication house, utilization may be a lower thing. Otherwise, utilization is a big factor. To answer your question, yes, to 60-70% of the case, it is an important factor, the number of cells in the design. Okay, so then area calculation, square, rectangle, rectilinear floor plan. I will be telling why rectilinear floor plan. Don't always think that your block is going to be rectangle or square. Okay, people will come and cut one portion of it and then tell this is going to be your thing. You have to go and do a replacement of all your ports accordingly. Why? I will tell you during the course, because I have to show the diagram. I have to clearly tell you why you have to have a rectilinear floor plan compared to a square or in case of need. Okay, that mainly relates to the partition question that you had. Okay, then power routing. Okay, all this is fine. You place all the cells. Who gives food for it? Power. Power strap is very important. Okay, you know if a current flows, definitely there is a resistance in the path, R factor. If it's a very thin net, yes, RC factor comes into picture. RC is nothing but the time constant. Okay, R into C, resistance capacitance. R equal to rho L by AC is equal to X naught D by D. Okay, that those fundamental school equations are all. That's why I'm telling electronics is important. And we have a tool to do RC extraction, and we will not be having it here in the institute because that is very expensive. That is called star RC. Okay, so star RC we will not be having. ICC will be extracting SPEF, standard parasitic extraction format, and it will be giving SPEF for you. Okay, so that SPEF we will be taking for doing our timing calculation. Okay, so now coming to the point, power. R is an important factor. So why R is an important factor? There is a very important terminology called IR drop. What is IR? Voltage drop. Okay, what is voltage drop? V equal to I into R. Correct. So voltage is nothing but I squared R. I into IR, which is called I squared R. Okay. So if a current is flowing, doesn't mean that you give the current, the 0.9 volt to 0 volt between the gate and the VDD connection. 0.9 volt to 0 volt, it flows down because it's a potential difference. Now, the current density, does it flow at the same speed everywhere? No. As it keeps coming, there will be dissipation. Okay. How you have to reduce the dissipation? Okay. That is where power routing comes into picture. Now, why should I be bothered if current drops a little bit? Why should I be bothered? Doesn't matter to me. It is because by the time it comes to open the gate for you, okay, the current density reduces. If it reduces, the gate opens slowly. If the gate opens slowly, that cell will work slowly. If the cell works slowly, will you be able to meet your frequency? What are we dying for? We are all dying to meet the timing end of the day. Okay, we will not be able to. Okay, so it's very important you have which metal layer, the top metal layer. Okay, understand the timing, metal 7, metal 9, you have to see how many metal straps have to be given, do the IR analysis. Okay, make sure every stage the drop is within limit. Okay, and taken forward, that is also a sign off check. Okay, so here we will be doing the power structure, but we will not be doing IR analysis because the tool is called Apache from Ansys. Okay, so Red Hawk, the tool is Red Hawk. So we don't have Red Hawk access here, but that is a separate domain as such. But within ICC we will be doing the power structure. You get it right? What it is?
Yes. Multiple designer will do the IR.
No, IR team will be there, separate. IR team will be there. So usually in companies, what happens is IR guys will give the IR structure to you, telling that use this metal layer, okay, and use so many straps, okay, and use this width for straps, okay, and it should have so many decap cells, blah blah blah, all these things. So we will be taking their protocol and then we will be implementing as a physical design engineer and take it. So as I told you, some of you might get into the IR domain. Okay, so I know a girl who's an expert in IR drop analysis. In and out, day in and day out, she does IR drop. Okay, so when it comes to timing or when it comes to CTS, she's little blank. Okay, but when it is related to IR, she's the queen there. Okay, that's because you will learn everything, but then you will get into a domain and everything is an ocean. Okay, and you will be concentrating only on that. Okay, so similarly there will be a dedicated, to answer the question, there will be a dedicated team who will be working on the IR analysis, and there will be an expert in Redhawk tool. Redhawk is the name of the tool from a company called Apache, which was acquired by Ansys. Okay, so need for power routing, types of power routing, power ground rings, straps, mesh, standard cell rail, RC parasitic extraction. Okay, placement of the cells, very important. Where do you place what? Macros, memories. Every design should have memory in it. Okay, so where do you place the memories? Different terminologies associated with that, like tie cells, high fan out net synthesis. High fan out means, what is a fan out? What is a fan? Again, I correct. Exactly. The number of things that's getting driven from one particular cell is called fan out, right? Now, again, that's an English meaning. What is a fan? A fan is nothing but you have a fan here, you turn it on, it widens out. Okay, it kind of spreads everything apart. Okay, a lot of so fan out is nothing but just, you know, multiple leaves to that fan that you have. Actually, fan is nothing but, in Japan you have seen, right? This fan that you open using a what is that? The attached leaves or something. Okay, similar to that. Fan out again. In my design, the biggest fan out net is dash. What is the dash? The biggest net, connection between one cell to another. Okay, which is the biggest fan out net in the design? Huh? Tell me. Yes, that's correct. Clock. Okay, so this is the thought that I want everybody to have. Clock is the biggest fan out net. I will be giving a clock. There will be a crystal sitting outside my chip. The crystal is going to be giving me pulses. The pulses have to be taken to every cell in the design. That's the biggest high fan out net. Okay, there are other high fan out nets like enable signals. Okay, to enable flip flops. Then reset signal. You're going and pressing a reset. Okay, your design chip has to come to a reset state. Okay, that is also a high fan out net. But reset tree synthesis, nobody has heard about it. Enable tree synthesis, nobody has heard about it. Clock tree synthesis, yes, it is the heartbeat because my chip has to work in the frequency. Okay, that is a heartbeat, that is a vein of it. That is the reason why clock tree synthesis is a separate entity or a portion all by itself. Okay, and that is why high fan out synthesis is not done for clock at this stage. You keep it aside because you have a big work to be done later, and that is why high fan out net synthesis here, if you see, you'll be doing it on all of the enabled region and all that, and coming to the other ones later. Scan, I told you I'll be touching upon little bit of DFT. I will not be going into details of DFT. Why I have to be touching little bit of DFT is because DFT has got a scan connection, okay, and there is a reason why setup is not checked for DFT, okay, and hold is a big factor for the DFT, okay, and the interconnect during placement is very important when it comes to DFT, and why that interconnect have to be reduced and how it is reduced. It is done through something called as reordering and repartitioning. Okay, it helps me save my routing connection. Okay, to know that you have to know little bit of DFT. That's why I told you in one session, maybe half of the session, I will be touching upon what fundamentals of DFT is. Okay, because I can very well do one thing. DFT will be done, so you go and do reordering. No, I will not do that. I will tell in what in DFT was done, which is having a problem for me in placement, for which I have to go and make changes. Okay, so I will be emphasizing on those things. That's what scan reordering is about. Okay, then guiding. Okay, so guiding is very important when it comes to high speed networks. I will tell you how to create route gates. Regioning. What is regioning? What is creating bounds? Again, English meaning bounds. How to keep logically talking cells close to each other. Those are all called regioning bounds. Again, English meaning. Okay, put it into semiconductors. Don't think it as a jargon word. Simple. Okay. Now, timing analysis and optimization. Setup will be checked at this point of time. Hold will not be checked. Why? Because hold has got very big association with clock tree synthesis. Okay, hold will never be checked at this point of time. You can go check it. Tool will not come and tell you don't check. Okay, but you can check it. But there's the reason why you don't want to check it. Then go to CTS. Spend your brains doing proper clock tree synthesis. Different ways of doing clock tree synthesis are there. Spine method, history method, mesh method. High-speed processors have something called a mesh. AMD predominantly uses mesh method. That is called MPCTS, multi-point CTS. Okay, there are various ways of doing clock tree synthesis. What is OCV? On-chip variation. Okay, on-chip variation. Okay, there can be variation in process. There can be variation in voltage. There can be variation in temperature. All these variations is going to finally have an impact on what? Timing. Again, that's why I'm telling you timing. P varies, timing gets impacted. V varies, timing gets impacted. T varies, timing gets impacted. Yeah, impacted. Now, what are the variations of P, V, and T? There is something called as scenarios or multi-mode, multi-corner. Okay, so I will be giving details of multi-mode and multi-corner, various aspects of P, V, and T. So I will I'll be giving you details of Six Sigma curve also. Do you know what is Six Sigma? Six Sigma is not proprietor of semiconductor industry. Six Sigma was designed or derived by Motorola and some other automobile company in Germany. Okay, it's a compliance. Okay, Six Sigma is nothing but a compliance. So they say Six Sigma certification. All you have heard about it, right? So I don't know if any of you have taken it. It's nothing but plus or minus 3 sigma. That's what Six Sigma here. So you have a Gaussian curve. You put on left side and right side. Okay, so that's how it is. Now why I am telling that here is PVT again will be distributed using this. Okay, how we have to put on the positive side and negative side, how we have to take those cells and take it in your timing design. I'm not going to details because those will be more clear and explanatory when we start looking into diagrams on the screen. Okay, D rates. Why we need D rates in the design? You asked the question, what is the difference between 10 nanometer, 40 nanometer? Okay, 10 nanometer, a cell is taking 20 picoseconds to go from input to output. Okay, I cannot take that the cell for sure that this cell for sure will take 20 picoseconds. No, because once it gets manufactured and once it comes, there can be different factors that will go into the cell that can make sure the cell can either become faster or slower. If the cell becomes faster, it's a problem for me. If the cell becomes slower, again it's a problem for me. Okay, that is why we have to give something called a D rate. D rate means 40 picoseconds is the time. I give a 10% D rate. 10% of 40 is how much? 4. So the cell can actually work in 44 or 36. Okay. Now, if the cell works in 36, it is good. Everybody thinks it's good. It is faster. My chip will work faster. No, there is a factor called hold. If a cell timing is fast, your hold gets impacted. Okay, hold is nothing but you have to. What is the definition of hold? Clock signal comes, data should remain for some time after the clock signal comes. That's the actual definition of hold here. Okay, so for this session, at least I'll give some analogy. You're going, train is at 5 in the evening. Okay, you're going to board a train in the evening at 5. Okay, you don't go exactly at 5. Okay, and step into the train when the train starts moving. No, you don't do it. Okay, you at least make sure you get into the train 10 minutes before. That's what is set up time. Okay, and you you make sure train is static for some time after you get into it. Okay, so exactly the same meaning. Okay, again you have analogy, you will be able to appreciate semiconductors in a much better way. Okay, same way setup and hold is very important, and setup is always dependent on the frequency. Okay, hold is never dependent on frequency, and that relation is actually why we don't look into hold fixing at CTS, pre CTS stage. Only after CTS we will be checking hold. Okay, and I'll be touching upon every detail of it, in depth details of all this. Okay, and that is why we need D rates here. Okay, routing, there's something called as global routing. We cannot do routing in one go. Okay, we have to go step by step. Okay, do something called as global routing, then you go on assign tracks, then after assigning tracks you move the metals so that it complies with the rules that's given by your foundry for physical verification, to check physical verification, all that. So it's very important we uh, do the stepwise routing, global routing, track routing, and detailed routing. Okay, final checks. So after everything is done, again some more checks are there. Antenna. Okay, again antenna. Don't think it's proprietary of semiconductors. English meaning. Antenna. What is antenna? Something that is long which can conduct. That is the English meaning of antenna. Olden days, I don't know whether you've seen. Nowadays you have dish and all that. Olden days you have something like aluminum things and like a lot of spines up and down. Correct. So that's similar to antenna. Anything that's long that can conduct. So I will give you details why antenna is a problem, why it can go burn a chip. Burn a chip in the sense burning of gate is very important. The factor is very important. The gate cannot get burnt. Okay, electromigration. What is electromigration? How can we avoid them? Okay, then physical verification, then IR analysis. I'll be touching upon the details of this. Okay, LEC. LEC is very important factor. Logical equivalence checking. So many things will be done, starting from the floor planning all the way till you finish your routing. You're adding buffers, you're adding inverters, you're making clock tree, you're changing clock tree, that this clock getting enable check, setup check, OCV, D rate, so many things, crosstalk analysis, crosstalk noise, crosstalk delay, everything is there. We learn all this, we'll become an expert in all this. Okay, after finishing everything, you're giving out netlist or you're giving out GDS. You go and put one small inverter in a path. Done. The chip is dead. Okay, wherever it's supposed to work the other way, it will be working this way. One inverter is enough for that. And how that inverter came in picture? It was an accident. Okay, because we are dealing with millions and millions of cells. People are doing ECO. Okay, so when people are doing so many ECOs, there'll be so many ECO cycles. People write manual ECOs. There's a limit to which the tool can do. After which, see, what is the IQ of the tool? Zero. IQ of computer is also zero. What you give, it gives out. Okay, it's all here what we have to do. Towards the end, all the big violations tool will fix. Towards the end, you have to go get yourself involved, open the timing report, see which cell you have to go, change, upsize, downsize, delete, remove, add. You have to do all that. When you're deleting or adding, if you go and add an extra inverter, gone. When you do such things, how to find it out? LEC, logical equivalence checking. Where do you check LEC? You have to have a reference, right? Okay, so golden, exactly. Okay, people who have worked on LEC will know. Golden. So what is my golden? I told you there will be RTL code. Okay, architect would have written RTL code. That RTL code is my golden now. Okay, who says RTL code is golden? Functional verification people will brand that RTL code as golden. Okay, they will brand. Only then your RTL code becomes golden. Then your generic netlist, your first level mapped netlist in design compiler, then your floor plan netlist, placement netlist, CTS netlist, routing netlist, everything will be different netlists in different stages. This netlist has to be compared against the golden RTL. Okay, if it matches logically, then this function, whatever is there in RTL, will be the same function after all your work. Okay, then you can say thumbs up, yes, my design is equivalent, it can work. Otherwise, there's something wrong. You have to go and debug what it is. Okay, again, to answer one of the questions, people do partition because tool does not have the capacity to do the entire chip's logical equivalence. It has to be partitioned and done. So there are some features called boundary optimization. For example, from one partition to another, there can be inverters that can get moved. So from top level, inverters moves from one partition to another partition. It is okay for me because it's just moving. It is not deleting or adding an inverter. But if it moves, the partition level, one inverter is missing. Other guy, one inverter is new. So this guy will fail, this guy will fail. But from the top level, they will pass. So there are a lot of such industry related details that you have to get into when it comes to logical equivalence checking also. So the point that I'm making here is logical equivalence checking is yet another thing. We will be touching over the concept of logical equivalence checking, but we will not be going into details of it because that's not going to be part of the physical design flow as such. Okay. We will just know what logical equivalence checking is. The tool is called Verplex, LEC tool from Cadence. Okay, that covers almost 60-70% of the industry's sign off, logical equivalence sign off. Okay, parasitic extraction, as I told you, star RC, QRC. These are the tools which will take TLU plus NXT to tell one unit length of metal has got so much of resistance, one unit length of metal will have so much of capacitance. Now, so much unit length will have how much? You have to extract. That is what is called as parasitic extraction. That's been done. It will be dumped out in the form of two things. One is called SPEF, standard parasitic extraction format, or SBPF, standard binary parasitic format. SBPF is more towards Synopsys. SPEF is a general common format. Okay. So why SBPF? Anyway, just because I'm telling this, I'll touch upon that. Tool, if you give everything to tool in binary format, tool will be very happy. Okay, it is like, you know, when you're having fever, okay, what people do, they mash porridge and they make it into a paste and give you, because you should not have the strain. Similarly, if you give anything in binary format to the tool can easily digest it, and then runtime will be lower, and the memory consumption, okay, will be lower. Okay, because huge servers will be running on for the tools, and the memory usage will be 250 gig and 300 gig. That will be the memory usage. Believe me, the laptop might have 16 gig. Okay, and we feel that's the best that we can, because that doesn't run any tool, but servers will be running at 200 300 gig. Okay, and huge designs, if the memory footprint has to reduce, we have to give conducive to the tool. That is why SBPF format has come, which is binary format of the parasitic one. Anyway, we will touch upon all this. This is just an overview class. I'm not going to details of it. I'm just keeping it going forward. Okay. Sorry. And two implementation projects, as I told you earlier, we will be taking it from the Floorplanning stage all the way to the timing. Okay. Okay, so synthesis I am not touching. That's what's been done in design compiler. Placement, where do you place the cells? Okay, tool will do the automatic placement, because you cannot go and place manually all a million cells. If you start doing, you'll do for 200 years. It will not converge. Okay, so we have to allow the tool to do. But what tool does? We have to go and check if it is correct or wrong. Okay, so there are multiple ways to check whether it's correct or wrong. We have to go and optimize it also. Then go to CTS stage, signal routing, and timing closure stage. Okay, floor planning. So if you see in this design, this is a simple example of a top level chip. So all these are going to be your IO ports. So this is going to be a corner pads, and this red one is going to be your power strap, which is going to be taking your power signals. This is going to be your IP. What is my IP? Intellectual property. It can be a RAM, ROM, PLL, anything. Okay, it is going to be, we call it as macros. Okay, so this macro is going to be, so as a floor planner, the option that you have in front of you is how are you going to place the macros? Tool will do to some extent, but a design on an average, one partition might have 30 to 40 macros, memories, PLLs, and all that. You have to go and place them on the periphery. Why on the periphery? We will look into it. There are reasons. Do an analysis, file an analysis, how it is connected, and check all those details of it. That is what is called as floor planning. So this is what is called as floor planning. Create the floor. How much of area is needed? Utilization. Okay. So usually we take this standard cell count. We give 35% or 40% extra to that, and that is how we come up with the structure. And that structure you can either make it squarish, rectangular, or rectilinear. Rectilinear means not exactly one portion of it is. Yeah, L shape, or not only L shape, you can have even a notch also. Why L shape? Any shape you can have. Okay, it's not necessary. Any shape. Okay, but it has to be, the shape cannot be diagonal. Okay, keep in mind, in semiconductor industry, tool cannot understand diagonal connection. Okay, if there has to be a diagonal connection, it has to be a small block, small block, small block, small block. If you keep small blocks staggered, that will show as a diagonal connection. But everything has to be a small block, because everything should have lower left coordinate, top right coordinate. If you have lower left and top right, it will clearly give you the rectangular or square or rectilinear coordinates. And in industry, it is that way. Okay, keep that in mind. Okay, your GDS is all about that. Okay, and everything has got a reference also. The reference is always LL. LL is nothing but lower left. We will go through it. Whether it is a chip reference or a cell reference or a IP reference or a macro reference, it is lower left. Okay, so this is what is floor planning. Placement is nothing but the placement of cells. Okay, now the standard cells are highlighted here. All the standard cells are kept. I have a very big doubt. I wanted that question from you guys. Okay, I keep on telling standard cell, standard cell, standard cell. Why am I calling standard cell? Okay, what is the need for me to use the word standard in standard cell? Why? Exactly. Height should be fixed. Okay. And there are many pressing reasons why height should be fixed. Okay. The reason is, if you see in this diagram, what do you see in this? The x direction is always static, constant. If you see here, the height of all this is static, the rows. Can you see that? All the heights are static, same. Correct. But the width of all the cells, one is big, one is small, one is really small, one is average small. Correct, right? That is why the height is same. Okay. And what is the fun in having height same? Again, there is a reason. Okay. Somebody doesn't want to keep the height same and play. If I can keep y-axis fixed and x-axis varied, I can also keep the other way also, right? But there's a reason, because there is something, you have a cell, there's something called as VDD and VSS rail. Okay, so what is a rail? You go to railways, you see the track, always there's a main, that there's a difference. Okay, the constant difference throughout the world, okay, throughout India or broad gauge or whatever it is. Similarly, you have the height same, which means it carries the VDD current, it carries the ground current. Okay, now when a standard cell goes and sits there, the standard cell's VDD and your rail will actually overlap, and your power is actually going to flow through that, through the source, through the gate, through the drain to the next cell. Okay, that is why we have standard cell. I will draw the transistor diagram and I will show you in detail how it is actually in the layout. Okay, I will show you the details. Okay, and Synopsys will give you libraries called FramView and CellView also. Okay, so why FramView is needed, why CellView is needed, okay, why we need internal details and why we need abstract views. Again, memory resources and runtime resources. So from this diagram, placement of the cells are done. Okay, and this is how placement is done, and these are the cells that are highlighted. Okay, why we need to highlight? We need to go and emphasize on some changes to the cell, some parameters, some attributes. Okay, CTS, very important. It designs how the arteries or the veins to your heart goes same way. Okay, how the pulses, clock pulses are carried from the crystal or onto the PLL phase lock looped onto every clock pin of the flip flop. Okay, how it has to be going there, why it should be balanced. Okay, why, what will happen if it is not balanced. Okay, what is positive balancing skew, what is negative balancing skew. Okay, how it impacts setup, how it impacts hold, how it impacts power, all these things. So when you're building clock tree, you will have lot of inverters and buffers in the path. You cannot have any other cell in the clock path. Okay, you can have provided you want to control the flow of clock. Otherwise, you should not have. There's something called unitness of cell. Okay, buffer is a positive unit, inverter is a negative unit. From this result, you can understand what is a positive and a negative unit is all about, right? Similarly, when a lot of buffers and inverters are added, what happens? 2.2 gigahertz my Snapdragon processor, okay, or my Intel i5 2.3 gigahertz. It runs at such high frequency. The clock pulse goes through all these buffers. If I have say 80,000 clock buffers in my path, every clock buffer will be ticking. Okay, so do I want all the clock buffers will be to source and sink current? If it's done, fine. What is going to happen? It is going to take power from the battery. End of the day. That is why clock tree building has got big association with power also. Okay, and we will go through details of how to reduce power and what are the problems that you will face if you reduce power when we have to look at timing all this, because it's a trade-off. You reduce power, timing might get bad, so you compromise on this side, timing might get bad. How to balance it? So we will go through every details of it during the CTS stage, multiple phases of CTS stage. Okay, routing. This is how the routing of it is going to be. Every metal is going to be differently color coded. What is going to happen? You will have the base layer. After the base layer, okay, base is nothing but your polycrystalline, your N-well, P-well, your transistors and all that. Then after that, you will be having a field oxide. Okay, then you will have metal 1. Okay, when I say metal 1, metal 2, metal 3, don't think that these are copper, aluminum, gold, and platinum. No, it is either copper or aluminum. Okay, if it is aluminum, it is aluminum. If it is copper, it is copper. Okay, so why I'm calling this metal 1, metal 2 is different layers. Okay, so base layer, all the P well, N well, and everything. Then you have field oxide, metal 1, field oxide, metal 2, field oxide, metal 3, like that. It keeps going all the way up till metal 9, metal 11, and all that. How much ever your foundry supports. So this is how the connection is going to be. So if you see, one of the pins is going to be this one, and another pin is going to be somewhere like this here. So it has to go through one of the metal, jump to another metal, then jump. Then so there is something called as vias. Okay, from one metal layer to another metal layer, or substrate to the first metal is called as contact. Okay, again in via is English meaning via, go through. That is what is via. Okay, that is why I keep always. That's it. In that case, you won't forget. Okay, so I remember my physics teacher earlier in school days. Everything he used to, give an analogy. So as kids, right? If you have an analogy, then we usually don't forget. So similarly, I usually tell an analogy like, or I won't go into big analogy or phrases and all that, but I will tell it's just an English meaning, very simple. Via, it just goes through contact. It doesn't. It's not a via. It is nothing but it is contacting to your transistor. That is why it's called as contact. Okay, so this is what routing. We will be going through the details of routing. Okay, and as I told you, global routing, track routing, and detailed routing. Okay, so metals will be poured in the sense virtually on the tool. Okay, they'll actually be laid. Okay, and actual connectivity is realized, and now you will be doing the timing checking checks again. Timing check. Yes. Is the heartbeat correct? Is there a problem with setup? Is there a problem with hold? Fundamental equation of setup is nothing but your clock has to come, your data has to come sometime before the clock. Hold is your data has to remain stable after the clock pulse. That is what is setup and hold. Okay, that is the general fundamental meaning. You go for an interview. Okay, interviewer might ask this as the initial 1% step. Define setup, define hold. That's it. Nowadays in interview, I never ask what is setup and hold because everybody knows. Whoever is coming for an interview knows setup and hold. And I'm not going to judge the person based on what he knows, the definition of setup and hold. Okay, so that's what. So timing is very important factor. It's an extremely important factor. Okay, so associated with timing is just not setup and hold, as I told you. Setup, hold, insertion delay, latency, uncertainty, transition, clock transition, data path transition, T rates, clock crosstalk delay, OCVs. Okay, then clock pulling, clock pushing. What is clock pulling and clock pushing? Okay, it sounds very normal English terminology, but a lot of electronics related to it and lot of mathematical analysis also related to it. I will be giving you the complete details with examples on what these are. CRPR, common path pessimism removal. Okay. Then another factor which I will definitely touch upon is crosstalk. So you asked a question. 180 nanometer, 130, 40, 65, then all the way till 20 and 10 nanometer, right? Crosstalk is a very important factor. Okay, so one net is going, another net is going by the side. Okay, you should definitely have a minimum gap, otherwise it's going to be tough. Okay, it is going to have a coupling capacitance between them. If it has a coupling capacitance, done. Either this net is going to become slower or this net is going to become faster. If it becomes faster or slower, either way it's going to be a problem for me because of setup and hold. Okay, setup and hold are converse. Don't think that if something is faster, it's always good for you. It's not necessary that your chip will work fast. Okay, you're given constraints, your design has to meet constraints. But it becomes faster, your hold is going to fail. Hold failure is bigger problem than a setup failure. Okay, so keep that in mind. So all this we will be touching upon in complete depth in timing closure. So I have seen physical design guys, they know the physical design flow, they will completely understand the physical design flow, but when it comes to timing analysis, they will kind of say probably this is going to be like this is going to be, I'm not very sure how it's working, I'm not sure how it's going to be analyzed this way and all that. Because static timing analysis, you have to put on your thinking cap a lot. You will open the timing report, you have to analyze the timing report. Okay, various n number of ways to analyze the timing report, and that is going to widen your knowledge. Okay, completely going to widen your knowledge on timing. You have to close on timing. Keep in mind, end of the day, timing. With just that in focus, you have to work. Fine, done. So the next one, ECO cycles. So what if timing is not met? So after finishing it in IC compiler, after you route the design, okay, you cannot, it will give out GDS. You cannot give the GDS to the fabrication house to create the silicon. Usually what will happen, fabless semiconductor companies will book a shuttle. Okay, so what is the English meaning of shuttle? Okay, companies have shuttle service, right? So meaning different people join together, take a chartered vehicle, and then go forward. Okay, to reach the destination. That is what's called a shuttle. English meaning of shuttle. Same way, TSMC also has shuttle. They will say in the month of October, this day there will be a shuttle. Okay, what does that mean? By the time you finish your design, you give the design to the shuttle with many other designs. Yours will also go in the same wafer. Okay, then it will come back. I don't want to go for full production because it will go in the shuttle, cost will be less, it will come back, you take that, put it into the tester. Okay, companies like Tessol and other companies will give you floors for testing. Put it into the tester, see if your chip is working. If your chip is not working, go make the changes. Probability that there will be n number of issues again. It's a cycle. Okay, same way, after you finish your routing, you cannot directly give, there are lot of problems. You have to call somebody who can certify, brand that my physical verification is fine. The tool is called Caliber. My timing is good. The tool is called Prime Time. My logical equivalence is good. The tool is called LEC, Cadence. Okay. My IR is good. The tool is called Red Hawk, Apache. All these people will have to do tick, 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 tick. Only then the GDS is of good quality, worthwhile quality, it can be given for manufacturing. Okay. Coming to the ECO part of it, timing part of it. If the tool is, if you don't see any violation, you take it to prime time starts seeing violation. then the prime time guy says, you did all the routing for me and you gave it. Now I see violation, what to do? Because I am doing extensive analysis. That's why what you didn't see, I saw. Okay, then you give me the fix. The prime time tool will run, create the fixes. Those fixes will now be taken into IC compiler and will be added. Then IC compiler again finishes everything, gives it again to prime time. Again, prime time will check. If their fixes are done, good. If it is not done, do second level of fixes, third level of fixes, fourth level of fixes. This is what is called as ECO cycle. In between, one factor is it has to be taken through RC extraction, because in this where is this? In this, if you see here, static timing analysis, all synchronous designs work on static timing analysis, meaning between a register and another register, you have to meet timing. Between this register and next register, you have to meet timing. That is what all this is about. Okay. Now, between two registers, you see that there is a data path. You can see, right? Now, the data path consists of cells and the net that connects the cell. So how to break it? The full path delay is broken into stage delay. A stage is nothing but a cell and a net. Okay. For a cell, you have to calculate the delay. For a net, you have to calculate the delay. For a cell, how to calculate what transition you give at the input and what load you see at the output. That decides the delay through the cell. Okay. For the net, how are you going to do? That has to come through RC extraction. That is where the RC extraction comes into picture. Okay, parasitic extraction. Okay, so that cell delay and the net delay will form a stage delay. Multiple stage delays will form the data path delay, and that data path delay will form the path delay, and that path delay, based on your frequency which comes to the launch and the capture, will decide the running frequency of your chip. Okay, so now you understand the ECO cycle, right? You have to take through the cycle. As you keep going through the session, complete detail, slowly one by one. By the time you finish, you will be an expert in all this. How it's working, how the ECO cycles and all. Okay. Fine. So now, clear with what it is, right? So this is exactly what we will be covering in depth, in detail in this session. So I just wanted to know, before I move on to other one, I think other ones are just purely on the tools and other things. So we can quickly go through it. So what I want to ask is any questions. Okay, any questions, any concerns you asked about partition, asked about technology and all. So any questions related to the course or related to what we are going to be discussing, or you want something else? You want to know whether we will be discussing that? Yes.
Related to the migration, suppose if you are designing some 50 nanometer or 600 nanometer technology, there will be some tools to migrate the designs. So will that be any part of it will be discussed?
No. See, migration is mainly related to, see, 150, 200, 350 micron to 28 micron people will not migrate. Okay. Migration happens between 19 nanometer to 65 to 20, 65 to 40, 40 to 28. Predominantly now what happens in the industry is 48 to 20. They don't have a design which happened 15 years back and they don't migrate now. Okay. So I will be touching upon small portions of how they migrate. What are the details that you know, just for you to understand. Nobody in interview is going to ask anything on the migration and all that. Okay, they will ask you what is the difference, what is the advantage, but they will not ask you to tell steps for migration. But in case if some guy who is doing migration who comes and asks about migration to you, and if you happen to answer that question, you will be a definite hire. Okay, but the probability of him asking is low. But we will discuss about those migration also, because that migration involves all the way from the design level till the final level. Okay, because the constraint is also a part of it. At the same time, the design is also a part of it. Okay, you have to migrate it. Okay, with the same example of the timing path I showed you, right? How the delays and how the constraint is, I will tell you how to migrate it.
But all is scripting
I won't be having any TCL session because I come with the assumption that you will be knowing the fundamentals of table scripting. Okay, so you can actually go to a Unix shell or a Linux shell if you guys have access to that. Okay, you can just put TCL as such. Automatically, tickle shell will open because any Unix or Linux comes with a ticket. So with that, online, even the institute's web page, we have certain tickle guidance uh, details and all that. Okay, fundamentals are tickle and how to do it. So you just go through it, create an object, loop through the object, dump out the object, make changes to the object, index the object, take out the index of the object. All these things you can actually do. Okay, so the examples will be in the form of set a apple, banana, orange, like that. Okay, it may be so trivial, but in that's needed for us because set A will be cell 1, cell 2, cell 3. Set B will be net 1, net 2, net 3. Is cell 1 related to net 1? Okay, and what is the connectivity between them? And what is the arrival time at this point? All those things we will be analyzing. Okay, but you will have to learn tickle by yourself. Okay, it's not a big deal. Okay, anybody with good intuition and good intuitive knowledge will actually grasp tickle probably in say a week's time, not more than that. But you have to. Okay, it is not like C, C++, Java or something where you have to go complete object oriented. Nothing like that. It's just fundamental set objects and get the objects, indexing it, looping it. That's it. Okay. To answer your question, there's a separate session for TCL. You can probably attend the session. Okay, I will not be touching about tickle. Get yourself equipped with these things. To be on the physical design domain, you have to know tickle. Okay, Perl I'm not telling, but tickle you have to. So any other questions?
Hello.
Any questions? Open up. Generic questions. Maybe after the session starts, we can go into in-depth. We can start from the basics. What is electronics? What is current? And I have to call what Ampere created long back. We can discuss, not a problem, because many people forget fundamentals. Okay, many people forget fundamentals, which is a very bad thing for us. And that's the differentiator between our country and other countries. Other countries, you see, guys may not be good in one thing, but they take something, they'll sit in the lab and they'll focus on that, and they'll get to the complete details of it. That is why, what is that, creation or definition of protocols and everything happened there. It is not that we cannot define protocols. We can define protocols. Why should all the protocols be defined outside? So tell me what protocol was defined in India. Why can't we define protocols? I'm very sure everybody, each and every one of you in the room can define protocols. You can. Only thing is we are not thinking. Okay, we don't get into that. We get into the loop of going to office. Somebody's asking me to do something. Finish that. Come back in the evening. My day is over. Next day rises, sun rises, sunset. Sun rises, sunset. No. So thinking is very important. Any other question?
One of the basic requirements for this curriculum.
Digital. That's why in one of the slides I showed you, right? So as I told you sometime back, TCL is important. Digital fundamentals are important. Fundamentals of transistors is important. I will give you the book names also. The books are available online, or you can go and buy that book, 200 bucks, 300 bucks, something. Okay. Online, I think it's available. Okay, you can download those books and don't go through all the chapters. I will tell you it's like chapter number 3. Okay, just go through only those chapters, some 40 pages, 38 pages or something. If you go through it, you will know the fundamentals of transistor. If you go through the complete one, it is for layout engineers. Layout engineers means people who do standard cells characterization and all that. You don't have to know that. Okay. So these are some of the fundamental things which you have to know. So once you start the program, I will tell you what you have to start with. Get yourself equipped before coming for the session. Okay, because asking questions is good, but proactively getting the answer before you come is anytime better. Okay, so I will be discussing mostly the industry oriented aspects connected to physical design, timing and all that, but you should do your proactive things before you come for the session. Anything else?
we are applying for an standard cell profile, log profile, like how important is the setup violation and hold violation being a layout designer or a physical designer? Much mandatory.
So you're mixing two things. Physical design is different from a layout engineer. Okay, so layout engineer creates the standard cells. Okay, and after creating the standard cell, he'll be creating nodes like DGSS, drain gates, or substrate. He'll be giving pulses to it, and then you'll be seeing the waveform and spice analyzer. Okay, waveform analyzer. Now, setup and hold for spice and spice doesn't know setup and hold. Spice is not an STA tool. Primetime is an STA tool. Spice is nothing but what you give as input, you get as the output waveform. That's all. It does not bother about anything else. But for me as a physical design engineer, after completing it, for me what is important is, am I meeting 2 GHz? Am I meeting 2.5 GHz? STA, static timing analysis between launch flip-flop and capture flip-flop. Okay, so that is what it is. For that, setup and hold is very important in physical design and in STA. But when it comes to a layout engineer, setup and hold is not important at all. Spice input waveform and output analysis of the waveform is quite important by creating a drain grades or substrate to all the nodes and creating a layout. Like you'll be creating PMOS, you'll be creating NMOS, poly crossing to the active region, creating a P transistor and N transistor. So one more thing which I wanted to know, you all know what is CMOS, right? CMOS. Why it is called CMOS? Why is it exactly? It is a combination of NMOS and PMOS. That is why it is called as a CMOS. Okay. But what does that C stand for?
Complementary.
Complementary. Okay. Good. So everybody knows the word. Now what is the significance? That is where people have to put on their thinking caps. Okay, and your physical design is completely associated with that. Okay, in an interview somebody asks, okay, what is CMOS? Complementary metal oxide semiconductor. Why? Because it's got a PMOS and NMOS. Okay, if you exactly, you're coming to the point. Okay, you're making it right. Okay, your thought is going in the right direction. Okay, because if it is an inverter, you have a PMOS, you have a NMOS. Okay, it is complementing to each other. Meaning, if it sources current through PMOS, it is 1. If it sinks current, it is 0. When it sources, sinking cannot happen. When it sinks, sourcing cannot happen. Okay, meaning it can function at one device, meaning PMOS can function, NMOS will be stopped. If NMOS is functioning, PMOS will be stopped. Okay, so this is why it is called as complementary metal oxide semiconductor, meaning if 1 happens, 0 doesn't happen, 0 happens, 1 doesn't happen. Now, going to one higher level, if you take a NAND gate, okay, there will be 2 PMOS in parallel, 2 NMOS in series. If 2 PMOS is in series, it is necessary that 2 NMOS should be in parallel. Okay, it is complementing. Okay, only then the sourcing of current to give a logic 1, sinking of current to get a logic 0. This is why it is called as complementary metal oxide semiconductor. Complementary. Okay, the definition of complementary comes from this. Okay, PMOS and NMOS. Parallel means series. Series means parallel. Sourcing happens, sinking doesn't happen. Sinking happens, sourcing doesn't happen. PMOS should function, NMOS should be closed. Okay, that is why it is called as CMOS, complementary metal oxide semiconductor. So these are things you have to learn. So that book which I will be telling you, okay, that chapter number 3, it will have all these details. It will have more details like what is the threshold voltage at which the gate opens, okay, what is the gate current, all these things, drain to source current, everything will be given in that. Got it? So anything else? Okay, I'll just go forward. We will be giving VPN access. If you have, I believe everybody has VPN access. Sorry, everybody has high-speed internet. Okay, you can connect through it, connect to the server, and then you will be given unique login. You can use the login, you can start working on it. Okay, so assignments will be there, course materials will be there, notes is what I'm calling as Bible, what you'll be taking. Okay, so I'm just putting a word to you from day 1, every word, okay, whatever is coming out of my mouth, please make a note of it. It's very important. All the trainers know. Okay, it is very important. If you just make a note of it, okay, in whatever way you can put a star side telling that this I made a note, but I'm not very clear. Maybe I go through it and I'll get it clarified. However fashion you want to make a note of it, you can make a note of it. But by the end of the course, if it is a 200-page book, if the 200-page book is getting filled 70 to 80%, have that very safe as your reference book. Okay, it will help quite a lot. In textbooks and in internet, you probably will not find details what we will be discussing in detail here. Okay, and I'll be giving small scripts. Okay, very small scripts. I'll not be going into details of big procedures to converge various things. Okay, small scripts to understand. Those things will be given to you in the labs. You can put it on the shell and you can run through it. So it's necessary that we have a mock. We need to have mock interviews because prep is very important. Preparation for the discussion with the and what happens is, don't go for an interview, attend the interview. You don't get through the interview, don't get rejected, because the guy who is taking the interview is also a human being. Okay, so he may be very specific in one particular domain. Okay, like for example, I'm very good in timing. Okay, and somebody comes for an interview, I will ask questions in a way where I'll have to judge how much of timing knowledge he has. Okay, I will touch upon other things, but timing will be my main focus. There will be some guy who might come in physical verification. He will be asking quite a lot of things in physical verification. Some guy will be good in floor planning. So you should know everything. Okay, and if a guy is very good in timing, and if you're not able to answer most of the questions in timing, don't get dejected. Doesn't matter. Okay, the other guy is there for you in some other company. Doesn't matter. Okay, right opportunities. Okay, guys who have not cleared 1 or 2 rounds, they have gone to the 3rd level, 4th level, and they got multiple offers later. Okay, doesn't matter. And there happened to be a coincidence where the guy who took interview came and joined this company as his teammate. Okay, so there can be like lot of churning up and down and all that. Forget about all that. Don't break your head into all that. Learn. Give full importance when you are here. Complete importance. Have a good night's sleep. Come with a fresh mind. Give importance to this. Learn and go. It will help you. Okay, if you do everything prudently. Interview questions. We'll go through some of these interview questions. Job prospects. Okay, sorry for this typo. I think autocorrect is very dangerous. Thanks. Why to choose a career in physical design? Okay, one of the promising things that's happening now at this point of time is physical design, at least in the last 2 years. Okay, and believe me, in this institute, okay, so it's like I knew the person here, and I just wanted to come, and it's not getting associated with the institute and working. So I get more involved with people who are in the younger generation who wants to learn things and then come up, and then who are entering the physical design domain, or who wants to explore opportunities in physical design. I will give that knowledge to whoever it is. At the same time, what is happening is I am still in the learning phase. What am I learning? So I'll be learning other things which is associated, which can help me widen my thought. Okay, I'm into physical design, I'm into CTS. That doesn't mean your CTS will go into a full physical design, will go into a full stream where DFT, everything comes into picture, which comes into a full chip, which comes into a board level. The board level comes into the app development, software development, which comes to a complete solution. Okay, laptop is a solution, cell phone is a solution, IoT is a solution, medical is a solution, aerospace is a solution, industrial automation, big time is a solution. Okay, so you go and do what you need in one portion of it and come out. Okay, and then try expanding. I'm not telling day one start expanding, but in 5 years down the line, 6 years down the line, you yourself will start thinking, what is it in that entire ocean I am contributing? Then I have to start looking into other options of the ocean, and physical design is one important portion of that ocean. Got it, right? Questions? Please, I want questions from everybody. Guys online, please, questions.
Hello.
Yes.
Hello.
Okay. Mainly electronics.
Am I audible?
So you don't have any electronics knowledge at all. No, now I have not touched upon anything. I just gave you the small tip of what it is. Okay. But as we go into details, you should know the fundamentals of electronics. That's why I told you, see, you can work as a physical design engineer. Okay. You will get a job also as a physical design engineer. Just being a person who does scripting and all that. You can be. I'm not telling no. Okay. You get a job. But my goal is much about getting a job for the guys. Okay, because you get a job, you start working 1 year, 2 years, 3 years, 4 years, then you will think, what is it that I'm doing? Am I running scripts? Am I creating scripts? There's much more to it. As a semiconductor professional, there is much more to microelectronics than just running as a software engineer. Okay, a software engineer, he does a code, the output comes visually in the screen. It's done over. Be it banking domain, be it what is that? Any other domain similar to that. It comes on the screen. It's finished. For you in physical design, you have a long way to go. You finish your work, you fold your hands and you sit. What we do is, after we finish the design, 3-4 months down the line, after the tape out is done, we call it tape out. Okay, after the GDS is given to the fabrication house, after 3-4 months, the chip will come back. You go to the tester, come back. What we will go and ask the manager is, has the chip come back? Is it working fine? Because my effort of creating floor planning or placement, the clock tree has gone into it. If the chip doesn't work for some reason, I am responsible for it. There'll be like 80 guys, no problem. But I am responsible for one portion of it not working properly. Okay, if it works properly, it's a celebration time. At least I feel proud of it. Okay, and that's how we have been brought on this, Raman. So to answer your question, you can be a physical design engineer. Okay, by running scripts, and companies will take. MNCs will take you and you can work, not an issue at all. But you have to learn. See, in this course, you will learn electronics. By the time you finish the course, you will learn about microelectronics. Okay, you learn fundamentals of what is needed for physical design. Okay, but you have to put an extra step or effort to know what it is. Okay, and that way you will be rated up. There are guys to support what you're telling. There are guys in industry in MNC who are working in the same team. Okay, who are not even engineering background. Okay, science background, but bachelors and masters with computer science, and they are working. Okay, so it's just that what you know. So we don't want to take a dentist and then make him a physical design engineer. No, right? So at least you should be able to appreciate. Okay, fundamentals of physics and mathematics. Questions, please. Guys, online, I heard somebody asking something.
I have joined very late, so can I have the recorded?
Sorry, it's very feeble. Can you come to the closer to the microphone?
Yeah. Are you getting my voice?
No, your voice is it's very echoing. It's very sunken voice. Can you just be a little more loud?
Can I chat my question?
Yes, please. No, it's clear now. Your voice is clear. You can ask. Okay, chatting takes a lot of time. Let's go with the questions and then yeah.
Okay. I have joined the session very late. So
Okay.
can I have the recorded session so that I can go through it?
That probably you have to connect to Srinivas so that he'll be able to give it. Okay, just connect to him. You should be able to give it. So there'll be a link that will be given to you, and you can actually connect to the link and then go through it. Okay.
Okay.
Sure. So were there any questions online? Sorry, I didn't go through the chat session as such. We're not audible. Guess I please fix so that we can ask.
Hello.
Yeah. So I think Anita Singh.
Hello, sir.
Yes, tell me.
Hello. So I don't have any pre-experience in TCL scripting or Unix. So
Okay.
how good should be my scripting skills before joining the course?
Yeah. So there is a session that's specifically for TCL. Okay. You will learn the fundamentals of TCL, but you will not be related to physical design for the TCL. So if you get the details of TCL, then you will be able to have your hands better on the lab sessions. Okay, so there is a training program for TCL also. You can connect to Srinivas. He'll be able to guide you, who can actually take you through the TCL program. Okay, but TCL is very important.
Okay.
So I have a doubt whether we are offering primetime STA hands-on or not, because it was mentioned verbally, but it was not mentioned in written anywhere. Prime time, see, static timing analysis prime time itself is an ocean. Okay, so this is specifically for you, Anita. So what happens is, if you get into prime time, there is a lot of things in prime time. Okay, static timing analysis is not a simple thing. Okay, there is statistical static timing analysis, there is OCV, there is parametric OCV, there is advanced OCV, there is a lot of in-depth details of calculation. There is something called as timing window calculation. Okay, PBA, GB, so many things are there. I will just touch upon what is needed for physical design, because if I start into details of STA, then STA itself will take weeks together. Okay, and STA career is separate altogether. Okay, people who are in STA, they will be completely immersed and involved in STA. So we will be working on the analysis of timing reports with the scope of doing it in physical design in ICC shell. Okay, we will not be opening upon prime time shell and working on it. Okay, does that answer your question, Anita? Okay, fine. Any other questions? Okay. Yeah. So OCV clock. Okay, I will give you details of all this. So Ranjini, I will give you details of what is OCV, in-depth details of what an OCV is, what are scenarios, multi-corner, multi-code, multi-corner, multi-mode, how companies like Qualcomm sign off the chips in 130, 140 plus corners, and what these corners are. That's when I was talking about the plus or minus Six Sigma and how it falls on both sides of the spectrum. Okay, so I will give you details of all that. Okay, with diagram and then with graphical explanation. Yeah, this is just an overview, Rajini. So your question is, your concern was that it was a little fast, but I believe I gave a good overview. Okay, is there anything that was not understandable from an overview perspective? I'm telling you, this is just an overview. Okay, I'm not touched upon anything. I'm just telling about what the course is about, nothing else. Okay, instead of you going through it, I'm just telling what the course is. Okay, in detail, when you go, you will be able to get the full in-depth details of every step. Okay, then I can be very slow. I can be even ultra slow to tell details. And if you ask questions, the better. Okay, one of you ask question, that will be helpful for everybody else. Okay, and we'll talk about around it. Okay, so to answer your question, Ranjini, we will go through details of it slowly. Okay, this session is not to get into details of everything. Correct. That's what. So physical design, you cannot be an expert in everything. Okay, you cannot be an expert in designing, synthesis, placement, floor planning, routing, CTS. You can't be an expert on everything completely. So as you keep going, you will slowly, in your career path, you will become like associate engineer, senior engineer, lead engineer, project manager, program manager. Like that, you keep going forward, right? As you keep going up, what happens is you'll be given more responsibilities. Initially, you'll be associated not even with the block. Okay, a senior engineer will do a block. You will go sit next to the senior engineer. You'll be helping on the block. Then you will be given ownership of a block. Okay, then you will be given ownership to two blocks. Then you will be given ownership of a subsystem. Then you will be given ownership of multiple subsystem from the top level. Then your top level will be given to you. Like that, your responsibility keeps increasing as you keep. And I'm talking about, like, as you keep going, like, 5, 6, 7 years down the line. Okay, so then therefore your career scales up as it keeps going up. Your career scales up. Okay, to answer the question, the growth in physical design is going to be like that. You cannot jump from day one to your full chip. Okay, day one somebody gives you a full chip, you're flat, done. You can't do anything. You'll be broke. Okay, fine guys. I think it's all fine now. So anything, just let me know. Okay. You mean course materials? Yes, there will be course materials will be provided as a hard copy. Hard copy. Yes. But that course material, see, I will open a slide. Okay. I cannot put everything in a slide. If I put like 150 statements there, I won't feel like writing it. You won't feel like even going through it. I'll diagrammatically put it. I will spend 15-20 minutes explaining everything. That is why I'm telling more than material, the one that you take note down, right? Or notes. That is very, 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 very important. Okay, very important. To make notes of every aspect. One slide, that slide will come as a material to you. It doesn't matter to you. Okay, if you think that you will get material as a hard copy, later on if you just go into it, if you just go, you will see that slide, and what we discuss in the slide, you might have forgotten. That's the reason I'm telling. Make note of it. Okay, it is going to help you in. It is going to help you in clearing physical design interview. Okay.
There is a separate session for fresher. So as a fresher, should I go for that or can I go in main?
What is that separate session for pressure?
There is a 4 week or 3 week session.
Okay, the fundamentals of TCL and digital design. Yes, if you are a fresher, if you don't know about digital fundamentals, electronics fundamentals, and all, you can go through it. Okay, mainly for TCL. Okay, it's important you know TCL. Okay, TCL you should have aptitude for programming. Okay, little bit of programming, not in depth of programming, not object-oriented, a little bit of programming. If you have that, then that will give you, a good insight into it. See, you go for an interview, somebody else comes for an interview. People who come without a TCL knowledge will also be called for an interview because they know something about some electronics and all that. But if you tell you know TCL and if you put in your resume that you know TCL, okay, you are not just one step, you're 2 steps forward because so much of work is less for that person in his company to sit and train you, right? Because you know, then he will say, you have any doubts? This is a user guide. You know, a little bit of TCL, go through it, develop yourself, that's it. Because you're step one step forward. Got it. So anything else? Questions, please. I want questions. I want questions. There are only 2 things which I can info. One, you know everything that there are no questions. Other thing is you don't know anything. So come up with questions. Come up with a lot of questions. Very important. Okay. What is the question is what is the main difference between front end and back end? Okay. Again, this is a high level English terminology, front end and back end. Okay. It is nothing but what you do here and what you do here. Okay. So in the entire ASIC flow, I will be going through the ASIC flow. So I showed you only portion of the ASIC flow now. So ASIC flow starts all the way from coding, designer, RTL coding. Okay. Then in parallel, verification coding using system Verilog. RTL code gets converted into gates. Okay. That gets converted into technology gates during synthesis. Till this portion is called as front end. Okay, writing the code and designing. A designer does not have to sit and know about CTS. It doesn't have to know. You go ask a designer. Okay, there are a lot of designers, architects. Okay, you go to Philips, you go to NXP, you go to NVIDIA. There are architects. Okay, those architects, their only job is to take the IEEE standardized protocols, write the RTL code. It's not an easy job. It's a tough job. Okay, because your chip, what is going to come in your phone or your laptop or your product, is dependent on how he writes the code. Okay, after he writes the code, he will do lot of checks and validation to make sure his code matches the IEEE PDF. Okay. Unfortunately, there is no tool in the world where you give a PDF and you get the code from. People have to sit and do it. Okay, there is no, unfortunately, there is no code. There is no tool. Okay, and I would love to see a tool in future. You give PDF and you get GDS. It is good, then it is very nice. Okay, read PDF and write GDS. It will be very good. Okay, but that's not what it is. So that is where front end and back end comes into picture. Front end guys do all this, does all this, gives it to the back end. What we do is backend portion of it. Okay, meaning start from Netlist, to take it into floor planning, placement, routing, CTS, do all the timing checks and give it out. Okay, and that's still lot of other backend activities. Silicon goes pre-silicon validation, post-silicon validation, testing. So many things are there after that. Don't think that what we finish, chip is going to be ready for it to be put on your board here. Okay, all this is important. Chip sits in the board. What will board guys do? Correct. There is something called as prototyping. Synopsys has got a tool called HAPS, high performance ASIC prototyping system. Okay. When somebody does a project for 1 year, same time the front end guys does the code. That code will go into something called as FPGA, Field Programming Gate Array. Okay. That FPGA will sit in your board. And once it sits into the board, in parallel, your Android development, your device driver guys, everybody will start coding it. Okay. Then later on, they will take out the FPGA, and by then you would have also finished your ASIC. Chip will come and that will sit in the board. Okay. So all this is mainly for the fourth cost function called time to market. Okay. Nobody is going to wait for every front end, back end, silicon validation, everything chip to come, then start writing a device driver. No. So this is what now you're able to understand, right? What is front end, back end, how it's in a complete life cycle. But for physical design, you have to concentrate on this portion, whatever I showed you earlier. That is a portion that you have to concentrate on. That itself is a big ocean. Okay, a lot of things to be learned, and I will be going through in-depth details of it. I'll be going through in-depth details. You have to be prudent. Any questions? People who have used physical verification, you should be having a lot of questions, right? So,
Hello.
yeah.
So, how does a physical design differ from normal custom layout design?
Normal?
The custom layout design, like
Custom
in
layout
physical
design, yes.
yeah.
Custom layout design, to answer in one statement, custom layout design does not connect STA with it. Physical design connects STA with it, meaning in and out you will be doing day in and day out, how to meet timing, how to meet timing, how to meet timing. My struggle is all about meeting timing. In the process of meeting timing, you will be taking through all the physical design flow. Okay, so custom layout design, they will be custom creating your standard cells like and or not inverter buffer, all these things, and then you will be going and characterizing it using spice analysis. Okay, and then you will be validating it for certain DRC LVS checks. Okay, and then making sure that cell comes as a standard cell to you. Okay, so custom layout is specific for creating very specific customized standard cells or macros, whereas physical design is the entire flow, more oriented towards more oriented towards digital and lot of association with STA. That is what is physical design is all about.
Okay.
Okay. Okay, guys, fine. So I'm closing the session now. So any more questions routed through Srinivas? Okay, I'll be able to answer the questions to you. not an issue. You can call me. If I'm not answering the call, I'll give a call back a little later. Okay, I might be connected to something else and be working there. So I hope it was a good overview for what we are trying to do in physical design. Got it, right? Sure. Thank you guys. Thank you online. You guys online. Thank you very much.